It's my pleasure to introduce the first speaker. Once she's all set up, I'll start. But yeah, one more minute. But well, she's Dr. Anna Goldenberg. She's local here. She's been in part of the Machine Learning for Healthcare community for a while. We're excited that she will be opening up this conference today. Well, I can briefly introduce her before she comes up. She is the first Barma Family Chair in Biomedical Informatics and Artificial Intelligence at the Hospital for Sick Children Research Institute. She also co-leads the AI in Medicine for Kids initiative and is a CIFAR AA Chair and a Fellow of CIFAR's Child and Brain Development Group. The focus of her research is on developing machine learning methods for clinical use across diseases and conditions, as well as quantifying the variability in the healthy state of individuals, as well as across populations with the help of wearables. She has also many educational roles where she develops and leads world-class educational programs in computational medicine and computational biology. So we're excited to have her join us today and open up this first session, just so that we all know what we are getting into. She will speak for about half an hour, then Dr. Sidnick will speak about again for another 30 minutes, and we'll open up the floor for questions after that. So please write down your questions, and then after both speakers have gone through their presentation, we'll open up the floor for questions and comments, okay? So with this, please, Dr. Goldenberg.
Can everybody hear me? Yes. Thank you very much for inviting me and for the honor of opening this conference. It's been one of my favorite communities, very close to my heart. And today I will talk to you about our journey to deployment. So we're all here, well, I mean, part of the reason we're all here is because we are very good at writing papers, but how do patients actually benefit from all of this paperwork, you know? So that's my goal. These are my affiliations. It's definitely more than U of T, where I'm a professor in both computer science and laboratory medicine and pathobiology. But I'm also at CKIDS Vector and CIFAR. So this project and this collaboration has started from the ICU clinician coming to my lab and saying, hey, so we have this case, can we do something about it? And what happened was, it was a 9-year-old who was skiing and they broke their femur. And they were helicoptered to CKIDS from out west, the mountains. We don't have mountains here. And it was delivered in time, femur was repaired, the surgery was successful, but in the process a clot has formed, and unfortunately this child has suffered cardiac arrest. And as it often happens with cardiac arrests, there was a long-term consequence of brain damage. And so there is no great way to be there on time to prevent the outcome. These things happen. So the real struggle here is to prevent the cardiac arrest from actually happening. So this is my collaborative project. And I could talk to you about this. We've written about this before. So the goal here is really to focus on the journey of, you know, the research to translation. So the fundamental question that we were asked was to predict cardiac arrest happening in the next 2 hours, and whether an intervention is needed. Yeah. And we had some pretty nice data, very sort of long-term time series. We had about 67 patients over the sort of retrospective years, over 6 years. And it was pretty good quality, I would say. So missingness under 20%, those of you who work in healthcare, you know this is gold. So had 8 signals. They ranged from respiratory to oxygen to blood pressure. And the way we defined labels was in communication with our dear colleagues. At that time, it was Peter Lawson, but also Jay Maswi, both of them in the States now. And we defined the pre-arrest range as sort of 2 hours before the pre-arrest range, and then we were taking half-hour windows within that range, and that was considered the cardiac arrest label. And then everything that was 5 to 6 hours before that, the range of that was split up into windows that were considered sort of the normal signal. And we had built some deep learning model, as all of us do. And the nice thing that we did was, as we were working, and we initially published a model that needed a lot of data preprocessing to use. We stopped with that. This model, you can just feed in the streaming data. And we are using masks and are awaiting calibration for dealing with the missingness. So that was very helpful. And then it was predicting cardiac arrest pretty well, I would say. We were able to predict within 2 hours to 15 minutes for about 70% of the patients, which is nice, right? The clinicians now have the ability to come there in time and make, put together a team and et cetera. So the clinicians said, okay, yes, we want to deploy. But in the deployment, as we started thinking and chatting more and more with them, there was this back of the envelope calculation. Okay, so cardiac arrest happens about 100 times per year at CKIDS. We have about 42 beds. So that's about, if we want to evaluate the model about every 30 seconds, it may be about 44 million evaluations per year of the model. If we have 1% error, that's 440,000 false alarms. Yeah. So we got terrified. We are saying, well, do you really need this model? I mean, like, why do you want to deploy this model? And they said, no. It's going to be useful because really what we think you are doing is you are predicting the risk of deterioration towards any critical event. This is not just cardiac arrest. We're using cardiac arrest as a proxy. That's what we are doing, and that's why we want this model. We want the prediction of cardiac, of risk of deterioration. The problem is that risk of deterioration is not a thing that clinicians label. There's no thing, oh, this patient has a 40% risk of deterioration, and that's somewhere in the data. It's not captured, it's not done, they don't do this. So we have to use proxy labels. So, and the data sort of a deployment changed a little bit. So we got the data over the last 3 years, and from the 42 beds before we had from 30 beds, and we had similar frequency with about 360 patients, but much more unbalanced than we had before. And the missingness rate was also like 40 to 60%. Yeah, so those of you know that this is much more realistic. And they said, well, these labels, they're not really going to work for us anymore because within 2 hours, if you are suffering an acute cardiac arrest, it happens in the last half hour. So all these windows that you have that are false positives within that 2-hour range, great. So we don't have the right data, we don't have the right missingness model, we don't have the right labels. So then Ismail, together with maybe here somewhere in the audience, the engineer who is a machine learning specialist who is working on the deployment team, together with the nurse who is in the unit, designed the true sort of labeling criteria, and they're going through this right now. So you can see it's a little bit more complicated. So these were the results of the model on top there. The precision and recall of 0. And we were like, no, this is not, no, there's bugs somewhere, okay? We were chasing bugs for a while. There are no bugs. This is just completely out of distribution of what we were expected to get. So we looked at the sort of no precondition, healthy heart prior, and some of the patients that were similar to our cohort with a similar sort of rate. And yes, we got a little bit worse result, but they were comparable to what we were sort of expecting. But the labels are wrong. The data is different. Everything is different. And so now we really are going through this process, which we thought we were pretty thorough in the beginning. We were working with clinicians all the way, but all of these things, right? The false positives, there are simple things in the data that seem ridiculous to us, but they happen. So one of the things was that in the notes, the time of cardiac arrest was recorded as Toronto time. But that same value was put as UTC time in the database. So we don't have the time. I mean, sometimes it's UTC, sometimes it's Toronto. We actually don't know the time. So there were a lot of false negatives. There was a cardiac arrest, but we considered it healthy because we didn't have the actual time. This was not specified. It was not it was non-trivial to figure out. So, and the definition of cardiac arrest sort of evolved over time, as you see. So all of these things, even if we are super thorough, they somehow come up at deployment. New things come up at deployment. So that's one part of the story. This project just keeps giving because it's sort of, we said, okay, we don't have a way to get the risk labels. Is there any way we can get the risk estimates of deployment? So what we did was we defined, together with my HCI colleagues, we defined a completely new interface that clinicians could interact with. So basically we asked them to estimate the risk when they're seeing the patient. And then at the next point, we're showing the risk estimates of the model and the previous ones, and they're able to drag that risk. Just with a finger on their iPad, just drag the risk and say, oh, it's there. And if they do that, they have to input the reason why they think the risk is high. So we can actually have the risk estimate and the reason for why, and what we are discovering is that of context that we're simply missing. There's no way for us to predict this without this context, but this context exists and the clinicians are using it to evaluate. So then there's a question of how do we actually properly collect the data that we can make the prediction that we're expecting to make. This was a wonderful project that actually Melissa McCradden, who is sitting here, and Shalmali, who is one of the conference chairs, were involved in together with my former PhD student, Sana Tanika Boni, to figure out what clinicians actually want to know from this. Okay, we have a model, we are making predictions, they can drag it up and down. But what happens in ICU is that after the fact, at the end of the day, they sort of look at all the cases and they're evaluating what actually happened to this patient, how could it be improved, the quality, et cetera. So what they said was, we want to know what features can tell us about what are the outcomes per patient that actually led to this increased risk. And sort of the temporal, the explanation needs to be temporal. And there were other things that they said that as far as I know, are not really being addressed in the literature and the research even, as far as that the older clinicians wanted they couldn't care less what AI does. They just said, if AI thinks that I'm wrong, it better prove to me that I'm wrong for me to listen. If it thinks I'm right, okay, I know I'm right, I'm always right. So, but for the younger clinicians, they said, no, we want to know that AI thinks that I'm right. I need this validation. This is very nice. It's like having a senior clinician on my shoulder. I love this. So actually, different clinicians need different things from the models to be able to use it and evaluate it. So then, based on that, Sana and Shalmali went off and together with actually David Duveneau and Kieran Campbell, we created a sort of risk explanation model or one of the feature importance, but the feature importance per time and per patient. So the idea of it is like this. We are thinking counterfactually now. So we have some model of the patient. We think this patient should, their risk should be A, based on what we have seen thus far, right? But it's actually B, right? And then the question is, how do we find a subset of features that actually led to a very different risk that was observed? So there are two components to the score, the feature importance score. One is saying, I want to see whether I can predict based on only the data up to time t-1, and how well can I do that? And the other part is saying, okay, what if I had knowledge of a subset of features at time t? How helpful are they, right? And so there are these two parts, the temporal shift and unexplained shift. And if these shifts align, that means the feature set is not important, right? If I can predict the risk or whatever I'm predicting as well using all the data up to t-1, as well as with the given subset at time t, that means that subset at time t is not really important, right? So then the feature importance is 0. So you can actually use this as part of your models to track back and say, okay, yes, there is this event that happened. What are the subset of features that most explain the variance, the difference in what we expected given what we see? And so it's hard to evaluate such models, and the way we evaluated was sort of taking the top 50 features of that were signified by our model versus all these other models that we all know and love. And it seems that our feature set was more useful for sort of the loss when you remove those features was higher. And then we said, okay, so we have all of these things. What do we do now? And then we collaborated with a systems professor who, together with our team, we have built a dynamic engine to be able to streamline all of the signals at the same time and make predictions in real time. And that dynamic engine is running now in sort of the silent mode, but has been running for a while. Okay, so that's great. So suppose we figured it out, and we now want to know what happens after. So the models deteriorate if you don't update them, right? So we have to update them. But what happens if we want to update the model, but the clinicians start believing the errors that the model is making? That means that these errors are actually propagating back as the truth, as the golden truth that we are training the model on. So what happens is that the model keeps getting more and more and more confident, the top line, more and more confident in the predictions that it's making, but the reality is it's actually deteriorating with respect to what it needs to be predicting. So we work on this idea of feedback loop. And there are two slightly different things that you need to worry about. One is error propagation, which is actually just flipping the labels. So suppose the labels were correct in the previous run, and now they're flipped to be wrong. And the amplification that once you do that and you actually make the prediction, it makes the model worse over time. And we have several papers on this, but I just wanted to give you a few lessons that we have learned. So the idea that this is just a linear model, and if you are only looking at the ROCs of your model, you will actually miss the fact that false positive. There's a trade-off, right, between all of these errors that we are making. And so over time, we are actually making more mistakes, but the ROC might look just the same. So the things that you have to monitor for your model once you deploy it have to be dependent on what you're measuring. This is sort of showing how depending on the trust of the user, so if the user is 100% trusting of the model and the model makes mistakes, that means that 100% of the mistakes will go back into the retraining of the model. And that you can see in the line in brown. Whereas if you have the 50% trust and the user sort of makes, I mean, we had to make some assumptions and we had to randomly assign which examples are being trusted, which are not. So there are nuances here. So for example, in my lab as well, we have work on the example difficulty. And so some examples are really difficult to predict, and which examples you can select to be able to improve on this. But the point is that the trust models make a difference, and how do we build the trust while actually making sure that the clinician is not fully trusting of the model because of the mistakes that we are making. There's a threshold selection of the model, sort of are we adjusting the threshold with time? And it seems that if, this idea that we can regulatorily approve the model and we don't touch it again until the next version comes out. And that's just not a really great idea for the models that are evolving over time, that need to keep updating. And the idea of setting more robust thresholds are basically fairly simple. You just model averaging, right? So you retrain the model, you take subsets of your validation sets, and you average the threshold so that you select the most robust one. This is almost too trivial to mention, but we have also shown that more complex models lead to more error propagation. However, you can help it with regularization. So this is taking the most complex model and looking at the simplest one, the dropout and the decay, and showing that you can actually use regularization for more complex models to fix it. But you can't just leave it, right? Because the error propagation is sort of the downward spiral. And yeah. So there are many things that we have shown to actually affect the model performance over time if you are updating. So the more frequently you are updating, if you are not monitoring the model, if you are just retraining happily with all these errors in the feedback loop, then the model will deteriorate over time. And of course, the higher the frequency of retraining, the worse it will be. But if you're monitoring, hopefully you are not propagating this. And there's a sort of this Malcolm Gladwell's point of deterioration, that if the error is very small, then it's not likely that it will deteriorate. So that's maybe some hope there. And yeah, so the idea is something that I mentioned before. You can use example difficulty to prune the set of the examples that you are using for your training, or you can use any of the techniques that have been published in the past. But it seems that if you remove, for example, positive examples and you retrain and you help with that, then you can improve the quality of the update. Yeah, so with that, I would like to conclude. I really wanted to talk to you today about the sort of the temporal noise label work that we have done. It's in review right now, and we are basically able to have some theoretical guarantees about how to change your loss so that you can improve the algorithm based on, even if the labels are noisy. But unfortunately didn't have time. Half an hour is not enough to talk about the field of deployment and all the problems and how to solve them. But yeah, so there are lots of challenges still, and there's a lot of work. I have mentioned some that people are not even working on yet. And a lot of them are related to the fact that we are not just doing this, because that there are constraints to resources and what can be done once it's deployed and affecting patients. Yeah, So we've done lots of other work. If any of you are interested, I'm happy to talk about. Interestingly, in medical imaging space, we actually had a project that's pretty much almost deployed right now as a silent trial versus a project which we have tested with the clinicians, and it took them longer to use the method for cancer detection as opposed to not use the method. And so we are not deploying that. But these are the kind of tests we sort of have to do to realize the deployment. A lot of the wearable projects that we've done have to do with heterogeneity of the population and the time series, and sort of can we extract useful causality from that data and use that in the clinic. So some of the papers are already published in that space, and some are forthcoming. Yeah, lots of interesting stuff in this field. So just skip this, and thank you, and thanks to my lab, which is absolutely amazing, and to my AI in medicine team, which is my deployment team, made of super high quality and amazingly fun engineers that are making it happen, and my collaborators. Thank you.